All right, class. Today we're going to look at salts in a solution and predict whether or not that salt will contribute to an acidic, basic, or neutral pH. So last time, or I guess two play posits ago, we talked about neutralization reactions and how acids and bases mix together to form a salt and water. So we're going to look at how that salt can affect the pH. This goes with acid and base chemistry number 5. So when we are looking at acid and base properties of salt solutions, we have to remember back to the solubility equilibrium part of that, the last unit, and how there's the common ion effect. Due to the common ion effect, when you have ions in solution, that actually can affect our pH. Because those ions can interact with water. So this particular topic requires a lot of backwards thinking. When we look at our salts, we have to try and think about what possible acids they may have come from and what possible bases they may have come from. So for neutral salts, my example here is sodium nitrate. If we think about where those ions came from, we're really looking at Na plus and NO3 minus. Well, if we have Na plus and NO3 minus, we can reason that these came from nitric acid and sodium hydroxide, which are both strong base and strong acid. So if we think about a strong base and a strong acid, we know those things dissociate completely. When they dissociate completely, we get a perfect 1-to-1 ratio. We could think about nitric acid and sodium hydroxide and forming sodium nitrate and H2O. The reason this contributes to a neutral pH partially is the 1-to-1 ratio, also because sodium nitrate is completely soluble. Since we have full dissociation, we know that all of the H pluses and OH minuses are going to result in water, and we know that water has a neutral pH. When we get dissociations that are affected by weak acids or weak bases, we know there's not full dissociation. So those ions floating in solution aren't necessarily completely neutralized, and therefore those extra ions in solution can contribute to our pH. So what I have here, just some notes, salts that are formed from the cation of a strong base reacting with the anion of a strong acid are neutral. If we're looking at the second example, we have salts that are formed from the cation of a strong base and the anion of a weak acid are basic. And now, if we think about that, we can look here. If we have K plus and we've got acetate, so C2H3O2 minus. What this really means is that we have KOH, came from KOH, which is a strong base, and the negative anion would be acetic acid. So HC2H3O2, and that is a weak acid. So sure enough, we've got strong base, weak acid. And if we just think about that conceptually, why might this be basic? Well, if we have a strong base, strong is always going to win. So we have a strong base and a weak acid. We know that strong base is going to completely dissociate, but that weak acid's not really going to dissociate as much. So you'll end up with a situation where you could have basically all of this OH hanging out here, right? And regardless of concentration, you might only have a few H pluses, right? The weak acid, you're going to have mostly HA. And that HA is not really going to react with your OH, but your one H plus will. So it makes sense that if we have a strong base and a weak acid, we've got to have way more hydroxide in our solution, and therefore when we have a salt like this, the solution overall will still be basic because we haven't quite neutralized everything. Now, the converse is also true if you think about salts that are formed from a weak base and strong acid. We are going to end up in that same sort of position. If we're thinking about our solution here with ammonium chloride, we know that the Cl- is probably coming from hydrochloric acid, which is a strong acid. And if we're looking at ammonium ion here, ammonium ion came from one of two things. It probably came from NH3, which is a weak base. All right. So again, if we have a strong acid and a weak base, well, you've got a whole ton of H+ hanging out here, and maybe only a little bit of OH from the water. Now, I know NH3 is confusing because that is still a weak base. It's going to gain a proton. Your weak base here technically is also, or sorry, weak acid also in here is going to be your water. Water is going to act as an acid in this situation here, but the stronger acid that we have is hydrochloric acid. So even then, you've got way more H+, and it's outnumbered, or outnumbers the hydroxide concentration, and therefore overall we're going to be more acidic. Okay. The hardest part is just thinking backwards about what those things possibly came from. If it's a positive ion, remember it came from a base. If it's a negative ion, it came from an acid. So you have to think back about what those things possibly could be. Typically, if you just throw an H on the anion, you find out what acid it is. Just make sure your charges are balanced, right? Nitrate ion is a 1- charge. H+ and NO3- would give you nitric acid. Whereas if I had, I don't know, like sulfate, the sulfate ion, for example, is a 2- charge, you're going to need 2 H's to form sulfuric acid. So just keep that in mind. Make sure your charges are balanced when you're going backwards. If it's a base, we're throwing hydroxide on it in most cases. That'll certainly help us there. So, and actually, if you wanted to, you could even consider instead of NH4+ going to NH3, it could also be NH4 ammonium hydroxide. That's another possibility. But either way, you still have weak base reacting with a strong acid. Okay. Now, of course, you probably figured out okay, so now, of course, you probably figured out that there's going to be some math involved. If we know that there's going to be affected on our pH, yeah, we certainly can solve for it. So whenever we read these problems, first thing we're going to have to do is figure out where the ions are coming from, and that will give us a big clue as to how we're going to set this up. Now, if it's a weak base or a weak acid, we're going to have to do some rice tables. If they're strong and strong, it's going to be neutral anyway, so it'll be pretty easy to see. All right, so first I know that Na+ is likely going to come from NaOH, which means this is coming from a strong base. Okay. And therefore, if I look at my F-, F- is going to come from HF. All right. And that means HF is my weak acid. All right. So the title of this is Salts as Weak Bases, because if I look at the neutralization reaction here, I end up getting a salt that functions as a weak base because it's the conjugate of my strong base, right? So if I look here, I got my reaction F- plus, I'm going to write water this way because it helps me to visualize, plus HOH, same thing as H2O. We're going to get hydroxide ions and HF. This is the equilibrium that we're looking at here. Okay, we want to see how water affects our F- concentration, and we're going to figure out how much hydroxide is going to form from that. Okay, so one of the other tricks here is that HF is a product on here, and they give us a Ka value. So we're going to have to do a little bit of a transformation. We know that Kb is equal to Kw over Ka. So if I grab my calculator, 7.2 times 10 to the negative fourth, 1 e to the negative 14th, which is my Kw, divided by 7.2 e to the negative 4. I'm going to get a Kb of 1.39 times 10 to the negative 11th. All right, 1.39 times 10 to the negative 11th. That's going to be important for later because this reaction, this is a base reaction, right? If it was Ka, we'd be showing the ionization of HF to form H+. Kb is showing the formation of OH-. Okay, so we're going to set up a Rice table for this. All right, so here's our R, here's our I, C, and E. Okay, well, our initial concentration of F- here is 0.30 molar. We don't care about water, and our initial concentration of each of these is 0. Okay, so knowing that it came from a strong base and a weak acid is going to be helpful in the long run, because when we conceptualize it, we already know that if strong always wins. So if strong always wins, is this going to be a more basic or a more acidic solution? It's going to be more basic because the weak acid is not going to dissociate as much. So we should get a pH greater than 7, and let's figure it out. We've got minus x plus x plus x, and when I do my equilibrium, x and x, put that together, x squared is going to be equal to 0.30 minus x, and that's equal to 1.39 times 10 to the negative 11th. If you look at that Kb, that is super, super small. I'm not even going to go through the trouble of calculating. 10 to the negative 11th is super small, and 0.3 is really large. I'm going to neglect x here. Once I neglect x, I can then solve for x. So 0.30 equal to, so that's a terrible equal sign, equal to 1.39 times 10 to the negative 11th. All right. I still have that in my calculator, so times 0.3. All right, and I'm going to take the square root of my answer. All right, 2.04 times 10 to the negative 6th. Okay, so x is equal to 2.04 times 10 to the negative 6th. Now be careful, is that my H plus or my OH minus concentration? That is OH minus. So if I do negative log of OH minus, I'm going to get my POH. All right, well that's easy. So let's do that. Negative log. Let's get my POH 5.69. Okay. So 5.69 is my POH. How do I find pH? Well, pH is going to be 14 minus my POH. So 14 minus 5.69, and I get a pH of 8.31. All right, so my pH is 8.31. Is that acidic, basic, or neutral? That's basic, which makes sense because strong base always wins. So if I have a salt solution with sodium fluoride in it, and know it came from the neutralization of a strong base and a weak acid, it is going to be slightly basic. Okay, let's do another one. This time we're looking at salts as weak acids. All right. So with salts as weak acids, we have to ask ourselves where these things came from. So first off, I can see right here that this probably came from hydrochloric acid, which is a strong acid. All right. So I can already tell just the fact that I have a strong acid and that NH4 came from a weak base. Which one's going to win? Strong always wins. This is going to be slightly acidic in solution when I get my final answer. My pH is going to be below 7. All right, so let's figure that out. I'm looking at the Kb. They give me a Kb value for NH3. So first I need to look at my dissociation. I'm looking at NH4 plus, and NH4 plus is going to ionize and give me H plus and NH3, which is my base. I'm forming my my base, but I'm also forming an acid, so I need a Ka value here. I'm forming H plus. If I was forming OH, I could keep the Kb value, but I'm forming H plus, so I need my Ka. So I've got Kw over Kb equals Ka, so which means 1 e to the negative 14th divided by 1.8 e to the negative 8th, or negative 5th, what was it? 1.8 e to the negative 5th. All right. I get 5.56 times 10 to the negative 10th. Okay. So this is going to be useful. 5.56 times 10 to the negative 10th. That's my Ka. All right, I have to set up a rice table. So same deal as last time. All right, 0.10 molar, 0, 0. This is X, this is X, this is minus X. You're getting so good at these by now, you could probably just skip the rice table part and go straight to this. X squared, 0.10 minus X equals 5.56 times 10 to the negative 11th. All right, and what are we going to do? We want to neglect X. All right, 0.1 is huge compared to 5.56 times 10 to the negative 11th. All right, so we can neglect X. All right, 0.1 times 5.56 times, sorry, did I say negative 11th? I meant negative 10th. Sorry. Woo! Gotta get my numbers straight. This is my Ka. 5.56 times 10 to the negative 10th. My bad. All right, so if I'm going to solve for X, 0.1 times 5.56 times 10 to the negative 11th, this really means X squared is going to be equal to, if I can write, X squared is going to be equal to 5.56 times 10 to the negative 11th. I'm going to do the square root of that, and I'm going to get an X equal to, times 0.1 square root 7.45 times 10 to the negative 6. Okay, 7.45 times 10 to the negative 6th. And the beautiful thing, this is my H plus. I don't have to do an extra step this time. So pH is equal to negative log of 7.45 times 10 to the negative 6th. Negative log, I don't need the second, negative log of second answer, 5.13. 5.13 is my pH, which is slightly acidic, like we thought it would be. All right. Another thing, just in terms of sig figs, when we're dealing with pHs, your number of sig figs in your prompt are going to tell you how many decimal points you need to go with for your pH. So we went to 2 decimal places here because we have 2 sig figs in each of our numbers. So hopefully I've mentioned that before. If I haven't, now you know. Make sure the sig figs are appropriate. 2 decimal places is appropriate for this because we have 2 sig figs. So 2 dec. Okay. Okay, so one of the ways we can figure out whether or not something will form a base or an acid, we can generally look at how they mix with water. So also getting into the acid-base properties of oxides. If you have a metal oxide mixing with water, it's generally going to form a base. So this is going the opposite direction. If we have our salt, we dump it in water, we're going to figure out what it forms. If we have a non-metal oxide and water, it's going to form an acid. So my example I actually have here is potassium oxide. If we mix that with water, it will dissociate, and we end up getting KOH. We get 2 KOH in there, and because our water splits up, we end up getting our 2 H's and our 2 O's. Yep. So we form potassium hydroxide. This one's a strong base. All right. Now my non-metal oxide example, if I have SO3, it's a non-metal, S is a non-metal, plus water. This will give me my sulfurous acid. That doesn't balance, right? Should be that. Yes. Okay. So I get H2SO4 from that way. The other way, if I looked here, I do this. It's H2O, and then I could get H2SO3. Okay. And we can look at that in class. I think this is one of the free response questions. Yep. That is all for today.